This is 8A.1.3 Arithmetic of Complex Numbers. Here we'll study addition, subtraction, multiplication and division first. Now, first we understand what is equality. When we say a complex number z1 is equals to z2, what we are saying is that the real part are equal. So A belongs to z1, the real part of z1. C belongs to the real part of z2. They are equal, as well as B and D. The B is the imaginary part of z1 and D is the imaginary part of z2. So only when all these four numbers are equal, then we say z1 is equals to z2. We now study some arithmetic operations, the addition first. In here, we're going to use I to represent square root of minus 1 instead of j. So please get used to the notation changes sometimes. Sometimes I is used as square root of minus 1, sometimes it's j. Here we say that z1 is equals to x1 plus iy1. And we say z2 is equals to x2 plus iy2. Now, when we want to add z1 and z2 together, the real part must add. So it's x1 plus x2, and I we put in front, and the imaginary part add independently, y1 plus i2. Similarly, for subtraction, z1 minus z2, we are subtracting the real part, x1 minus x2 plus I, y1 minus y2. So addition and subtraction behave in this way. What about multiplication and division? Well, let's try. z1 times z2. So this dot is not the dot product. This is the multiplication symbol for complex numbers, or sometimes we just write as z1, z2, and we don't use the dot. Well, we'll put z1 here, and we'll put z2 here, and now we open up the brace such that we can cross multiply the term together, which is x1 times x2 minus y1 times y2, because it's I times I is I squared, which is minus 1, y1 times y2. We then have x1 times y2, so it's x1 times y2 with the I in front, and now we have I y1 times x2. So this is the real part, and this is the imaginary part after we have collected the terms together. It looks like it's quite difficult to perform multiplication in the rectangular domain. Later on we'll show you that it's actually simpler in the polar notation to perform multiplication. What about division? Well, we have z1 divided by z2 is x1 plus iy1 divided by x2 plus iy2. You can work it out, and this is the answer. And again, you'll realize that actually it is quite difficult to derive this equation in a rectangular form. We'll show you that it's actually simpler in the polar notation. Now, if you all want to try to derive this equation, then the idea is this. We multiply x2 minus iy2 over x2 minus iy2. Since this is the same at the numerator and denominator, you realize that this is value 1. Now when you cross multiply, you'll get this result. I'll now show you what addition and subtraction means in the complex plane. This is vector addition, and this is the complex plane. This is the real axis and the imaginary axis, and we have z1 plus z2. So z1 is 3 plus 1j, so it's 3 along the real, 1 along the imaginary positive. z2 is 1 plus 2j, 1 along the real, 2 along the imaginary. When we add together, of course you can say that 3 plus 1 is 4, and 2 plus 1j is 3j, which is this number. How is this done graphically, geometrically? Basically, we take this factor of z2 and we move into here. So this whole vector is moved to the tip for addition, and the resultant vector is z1 plus z2. What about vector subtraction? Here we are doing z1 minus z2 over here. So what is minus z2? Well, if we have z2 as 1 plus 2j, minus z2 becomes the vector opposite to himself, to itself. So we basically flip this to the other way around. It is minus 1 minus 2j. Now we take this vector and then we add this vector to the tip of z1. So it's z1 plus minus z2, which is z1 minus z2, and this is the resultant vector over here. So vector addition is simply taking the other vector and putting it to the tip. Vector subtraction, first flip the vector that is being subtracted from z2 to become minus z2, and then moving this minus z2 to the tip of z1. So that is the interpretation of addition and vector subtraction. Thank you.